irrational numbers. So remember on irrational numbers that they're real numbers. Even though they're irrational, they are real numbers. So let's just review. If we had a square root or a radical, remember, so the square root of 90 is irrational. It's an irrational number. It's a radical, but it's irrational. Okay, so radicals can be either irrational or rational. Now the reason why the square root of 90 is irrational is it cannot be written as a fraction. Remember, it has to be written as a fraction, like a over b, where b can't be 0. Sometimes we write it as p over q. Right? So we have the square root of 90. We know it's irrational, but we can break down the square root of 90, and we can break it down to the square root of 9 times the square root of 10. Bring that up a little, because 9 times 10 is 90. And we did this in the last video. And we know the square root of 9 is 3, and the 3 is free of the radical. And then we have the square root of 10. And we can't do anything more to the square root of 10. Now if you said, well, the square root of 10 is the square root of 5 times the square root of 2, that it is true, but you can't break down the square root of 5 or the square root of 2. So it's easier just to leave it like that. Unless you can break down the square root into a perfect square, or where 1 is a perfect square, don't bother even breaking it down. For example, let's say you had the square root of 90, erase this, and instead of saying 9 times 10, you did the square root of 30 times the square root of 3. Well, you can't break the square root of 3 down. The square root of 30 you can break down, but you're not going to get anything that can help you, because you get the square root of 6 and the square root of 5. And there's nothing to do with those either. So it's important to remember this. When you have a radical, or a square root, you want to try to find where one of them is a perfect square. Now, if you get where one of them is a perfect square, you can free up one of them. Now, if we go back about 600 years before Christ, we go back to a man named Pythagoras. He had a student whose name was Hippasus. And Hippasus is the first one, what the myth says anyway, that found out about irrational numbers. And he was talking about the square root of 2, which we'll talk about in a minute. Now, the followers of Pythagoras did not believe in irrational numbers. It didn't make sense to them. So the myth goes that Hippasus was drowned at sea for actually believing in it. We'll come back to the square root of 2. Here are some of the most famous ones, and we talked about this in a previous video. We have phi, which is and again, some people say phi. It's the golden ratio. It appears in nature. It appears in music and architecture, and we'll talk about the golden ratio. We'll have a separate video just on the golden ratio. And of course, pi is probably the most famous one. 3.14, 15, 60. It doesn't end, right? None of these end. They just continue. And we have Euler, Leonard Euler. This is from his name, and it's the Euler number. And we have at about 2.718. Remember that ellipsis continues. Oh, and pi we did already. And phi is about that's pi. Phi is about 2.618. Roughly that. Continues forever. Now, it's important to remember about radicals. They are real numbers, like I said before. They're not imaginary. And we will talk about imaginary numbers. Remember, the square root of negative 25 is imaginary, because there's no two numbers that make the square root of 25. The square root of 25, negative 25 that is. The square root of 25, we said, is 5 times 5, or negative 5 times negative 5. But there are no real numbers that will give us negative 25 if we multiply the same two numbers. That's why negative 25 is imaginary. Right now, the only thing you need to know is if I ask you, give me an example of an imaginary number, just give me any number that has a negative in the radical sign. Any number. And this is what they say, that's the symbol for imaginary. So again, irrational numbers are real numbers. They're real numbers, but they do not terminate. They don't end. And they do repeat, but without a pattern. The pattern doesn't continue, right? It's just any random numbers. Right now, there's a computer in Tokyo, and there's many other computers around the world, who are trying to find out if pi ends. And right now, they're actually probably up to the quadrillionth place. Okay, and so again, rational numbers don't fit this pattern. It can't make a fraction, a over b, or again, p over q. But they are real numbers. Remember the symbol for real. Irrational numbers are real numbers. So let's use an example here. We've done this before in previous videos. If I had 0.717, 117, 1117 with that ellipsis, there's no pattern here. It seems like there's a pattern. It seems like you're thinking the next number will be 1111. That may be true, but it doesn't repeat. In other words, it doesn't go back to just a single one. Since this doesn't repeat with a pattern, this is irrational. But one we will talk about now is the square root of 2. Where do you see the square root of 2? We'll see it if I make a square. Make a square here. Right? And let's say it's a unit square. So remember, unit means that it's 1 on each side. Everywhere you go, it's 1. So if I wanted to find the length of the diagonal, we know this is a right triangle. Squares have right angles. And with Pythagoras' theorem, the Pythagorean Theorem, which we went over in 7th grade briefly, we know that if we had a squared plus b squared, I'll bring this over. Bring that over. If we had a squared plus b squared, we will get c squared in the Pythagorean theorem. So here we have 1 squared plus 1 squared, and that should give us 1 plus 1, which equals 2. So c squared means it's 2. But we don't want c squared, we want c. c will be the square root of 2. So the diagonal of a square, of a unit square, or the hypotenuse, this is called a hypotenuse, is the square root of 2. And the square root of 2, bring it over here, square root of 2 is roughly, remember it goes on forever, it's roughly 1.4142 forever. And you might be saying, well, if it goes on forever, how could it end in a diagonal? Well, it doesn't really end. We're getting as close as we can to the square root of 2. So let me just draw this again. Here we have a square, a unit square. And we want to find the diagonal. We can do it with the Pythagorean theorem. A squared plus b squared equals c squared. And if it's a unit square, it's 1 on each side, so that's 1 squared plus 1 squared, and we know 1 squared is 1, and 1 equals 2. Now, in the Pythagorean theorem, we have the lengths a, b, and c. Remember, c is the hypotenuse. That's c. So we don't, this is c squared. We just want c. So if c squared is 2, if c squared equals 2, then to get regular c, we need to do the square root of 2. And that's what it is. So just remember the diagonal of a hypotenuse from a unit square is the square root of 2. So that's irrational numbers. Great job.